In my presentation, I'd like to focus on different challenges that are still remaining in the field of processing big Earth observation data. And yeah, to face these challenges, we have implemented a distributed system architecture within a research project that focuses on the processing and using of Copernicus data for water monitoring. So first of all, I'd like to introduce the project goals and the motivation, and then I will come to the different challenges and the approaches we have developed within the project. Yes, actually, in the last years, the intensification of agriculture and an increased number of extreme weather events has led to increased sediment and material inputs into water courses and dams. For example, a frequent fertilization caused nutrient contamination in water bodies, heavy rainfalls leads to washouts of agricultural areas, and in addition, soil erosion affected in increased sediment deposition. So water authorities and suppliers had to face different challenges regarding the quality control of drinking water. There is a need for an improved water monitoring program, and in addition, there is a need for strategies to reduce the pollution of water bodies. And yeah, all these needs and problems are addressed within a research project, which is called WaCoDiS. It's an acronym in German for Copernicus-based services for monitoring material inputs in water courses and dams. It's funded by the Federal Ministry of Transport and Digital Infrastructure as part of the mFund program. The mFund program is a funding program that aims to support researchers on novel mobility solutions. The Wupper region is the area of research within our project. It's located in North Rhine-Westphalia in Germany. And the Wupperverband is the responsible water authority in this region. It operates several river dams and sewage treatment plants, and it also manages a whole sensor network for in situ data. And yeah, all these problems I've mentioned before are still are also challenges and problems the Wupperverband has to deal with. So the Wupperverband is one of our practical partners in the project. And yeah, related to these problems, main goal is the development of an improved water monitoring program that comprises different aspects. We want to provide an advanced environmental monitoring by providing different analytics services and EO products that can be generated and provided by the use of Sentinel or Landsat data. In the bottom, we see some examples. Classical example is a detailed land classification, which can be generated from Sentinel-2 datasets. Another example is the analysis of the change of water-land borders, which can be generated from Sentinel-1 radar data. And all these different products can help to improve water monitoring. We also want to combine in situ and remote sensing data in order to optimize hydrological models. Those models usually rely on in situ data, but those data have only a low coverage. So if we combine those data sets with remote sensing data, we are able to improve those models, which we are using as a project for sediment transport and erosion modeling, or for simulation and nutrient pollution. Yes, and one of the last goals, one of the main last goals is integration of the WaCoDiS platform, the Copernicus data and exploitation platform in Germany. It's a main entry point in Germany to Sentinel datasets, and this platform also provides a processing environment. And in combination, all these aspects helps to geolocate and quantify material outputs from agricultural areas. In the beginning of the project, we had several project interviews with expert users from the Wupperverband to get in touch with the needs of those users when talking about EO data products and big EO data processing. And as a result, we found that there are still several challenges remaining when bringing together the different parties that are involved in EO data processing. On the one side, we have the domain users which use EO information for their domain problems and usually integrate their EO products into their custom applications to get insights in their domain-related problems. But most commonly, those users have only a low expertise in EO data processing. On the other side, we have the EO community with high knowledge in EO data processing, which they provide in shape of processing algorithms and processing workflows. Usually they have no comprehensive understanding of the domain users' problems. And last but not least, we have the cloud platforms which have implemented in the last years different solutions for the EO data storage and EO discovery, and also provides a computing platform for online processing of those data sets. And yes, our project, the project WaCoDiS, aims to bring together all these parties which are more or less separated. The main question is how we can provide the EO products to the domain users, which are within our project, the users from the Wupperverband, because most of the users don't have any knowledge in how to process of observation data, and most commonly the usual workflow is searching the data on the platforms, downloading the data, load the data into their own GIS, and then process the data locally. Yes, the answer to the question how to facilitate the use of the EO product is to automate the processing workflow. And that is a thing what we have done in WaCoDiS. We have implemented an automatic workflow for processing EO data. And the first step in such a processing workflow is that the user provide a description what product they need. This description covers different aspects like for which area they need a product, which product they need, in which time interval they need a product, and in which backend do they need the product ingested. Second step is that our system, the WaCoDiS system, takes the process description and starts the scheduling of the process that is responsible for generating a product. At the same time, we have another component that discovers external data sources for new data sets to find those data sets that are required for generating a certain product. So as soon as the required data sets become available, the scheduling component of our system is notified. And if all preconditions are fulfilled, which are in particular the required data sets are available and the execution time is reached, then the execution is started. For the execution, the data sets are fetched from the data sources and are used as inputs for the EO processes. The EO process then generates the EO product, and this product will be automatically provided within a standardized web service, for example, an OGC web coverage service, but it could be also a web image an image service from within the ArcGIS image server. And those services are located within the domain user's environment, so the domain users can then access these datasets, the products within their own environment, and maybe use these services which provide the product in their own applications. Yes, and that's the whole processing pipeline, the whole workflow we are covering within our WaCoDiS system. The process workflow I've presented is placed within a microservice architecture, and within this architecture we have different components which handle the single process workflow task. If we have a look on the diagram, you see in the middle the main WaCoDiS system. You see there are different components, and all these components handle the different tasks. We have a job manager which provides an API to the users to define the job descriptions. We have a core engine which is responsible for scheduling the processes. We have a dedicated data source observer which discovers the required data sets in different data centers, and we have Meta's data storage to reference those data sets and to provide basic information about the input data that will be used for the processing. And on the right side, you see the processing environment. In this environment, the EO processing tools are deployed, which are wrapped via a standardized web processing service interface, so that we have a standardized execution of those processes. And in the top, we have the water management environment where the domain users are located. And in this environment, the products will be automatically injected in some services that will be used from the domain users. For the definition of the EO processing task, we have developed a domain model. You can see an example on the right side, and this domain model covers different aspects, different spatial and temporal aspects that are related to the processing. There's a definition of execution triggered. Execution trigger can be event-based, so that the process will be executed if new data sets are available. Such an execution trigger could also be pattern-based. Here we use cron-tab syntax. In this example, I think the process will be executed on every first day in a month and midnight. We cover different spatial temporal aspects like the area of interest, which can be defined as GeoJSON bounding box. And in addition, the input data that will be used for processing, for generating the products can be defined. You have to define different criteria that are related to specific data sets. Here in this example, we have an input data set, essentially 2 input data sets, and there are some specific criteria that are related to it. For example, the product level that is needed, or the maximum cloud coverage for this input data set. And with this with this description, our components are able to search for the required data sets in the data centers. Yeah, let's have a closer look on how we approach the interoperability in EO data processing. The question is, why do we need interoperability? In the last years, there have been arisen different cloud platforms for Earth observation data, and these platforms also provide a scalable computing environment. Most of these platforms allow the deployment and execution of algorithms that have been developed by the users. So if you want to include those services, those tools, and different cloud providing platforms into our architecture, we have to ensure the interoperability across the different platforms and for different tools. So we have decided to wrap the processing tools and services by an OGC web processing service. The service provides a standardized interface for synchronous and asynchronous processing job, and it allows, in addition, the definition of inputs, outputs, and processing parameters in a standardized way. So within our WaCoDiS system, the WPS instances are the main entry point to the EO tools, which run on which could run on different cloud computing environments. Each WPS process is related to a certain EO tool and encapsulates the execution details. So the remaining WaCoDiS system and yes, any other client that wants to interact with the WPS can trigger those tools then in the cloud. So with our WPS approach, we have a standardized way for the processing of AO data in the cloud. And in addition, we can also introduce new tools because we use Dockerized tools to deploy them in the cloud. And if there is any new tool, you can also Dockerize this tool, deploy it to the cloud, and make it available with the WPS. The last step within our automated workflow is sharing the EO products with the domain users. And to achieve this, we comprise in our architecture a component that automatically ingests those services into the infrastructure where the domain users are located. And our goal was to provide a flexible solution that supports any infrastructure. So yes, you can see here two different spatial data infrastructures, and within the spatial data infrastructure A, we have a product listener that is ready for injecting the data sets into a GeoServer backend, and in a spatial data infrastructure, we have another product listener which ingested products into a GeoServer or ArcGIS image server backend. In accordance to the event-driven approach of our system architecture, the product listener subscribes to a message broker in our system for new products. And if the new product has been generated by the web processing service, a new message will be published via the broker, and each of the product listeners get a notification that the product is finished and can be fetched from the web processing service. So the product listeners will fetch the data sets, the ready products from the WPS, and then will ingest these products into the back ends automatically. If domain users want to utilize EO products within their application, they have to trust into the generated EO information. For example, if they want to reuse land cover classification for hydrologic modeling and simulation, they must be sure that the land cover classification is valid within a certain area. So the information, the produced information, must be shared in a way that allows its reliable utilization for domain tasks. And this leads to different requirements regarding the reproducibility. Regarding the reproducibility of the generated EO products. And to support this task for the users, we have to provide different meta information for the EO products, which covers different aspects like spatial temporal coverage, information about the service where they can get the product, and of course the description of the underlying algorithm and the input data set that were used for the processing. So for each generated product in our system, we also provide some additional metadata, which you can see here in the example on the right side. And this metadata set covers all these aspects. We have an area of interest, we have a time frame for the generated product, but we also have references to the input data sets. And with this reference, you can get information about the data sets that have been used for the processing. And we have also the reference to the WPS process. And with this reference, the users can get information about the underlying algorithm from the WPS. Of course, we have a microservice architecture, so there are different deployment patterns. Up to now, we have set up a Kubernetes environment on our own server with a Minikube, but it would be also possible to use infrastructure as a service or platform as a service providers. More interesting is our concept for using the Copernicus data exploitation platform in Germany. It provides access to Sentinel and Landsat collections via virtual machines. So you can order computation resources, which you can use for different virtual machines. And we use it for the processing in our project. We have one virtual machine which hosts the WPS, which provides external access to the services. And we have another two virtual machines for running predefined processing scripts, which are a subset of Sentinel toolbox operators. And in addition, running the custom developed algorithms for creating the EO products. Up to now, we are still, it's still proof of concept because the WaCoDiS platform has been relaunched in April in this year. So we are still working on the integration. Yeah, in conclusion, our WaCoDiS system facilitates the use of Earth observation information for the domain users from the Bucur and supports them for water monitoring tasks. We have an automatically processing and provision of the product for the users. Due to our WPS approach, we have no vendor lock-in when we are using different EO tools on different cloud computing platforms, and the provision of detailed processing metadata contributes to the product reproducibility. There are still some open tasks within our project. We have to validate the system as part of a pre-operational deployment with the Wupperverband. We have to evaluate the WaCoDiS deployment concept, and we still have to take into account accuracy information for EO products, which can be also included into the metadata we are providing together with the products. Yes, that was it. Thanks for your attention. And if there are any questions, feel free to ask them.